Hello, everybody. Welcome to this new season of the JuantHEP Seminar, Quantum Computation and High Energy Physics. I welcome you on behalf of the organizers, Andris Ambainis, João Seixas, Simone Montangero, and myself. It's a great pleasure to welcome Elías Combarro from the University of Oviedo, who will be the first speaker of this second season of our JuantHEP seminar. Elías is a mathematician and computer scientist who has been studying, amongst many other things, quantum computation and its contributions to algebra and computability, etc. And more recently, he's been very involved in investigating quantum algorithms for high energy physics, in particular in collaboration with CERN, where he spent last year, I think, visiting. So Elías, welcome. Thank you very much for accepting to give the talk, and please go ahead. So also we have participants both here in Zoom and in YouTube, and we'll take questions in the end after the talk. Thank you very much, Elías.
Thank you. Thank you. Thank you for your kind introduction, and of course for this invitation. I must say that this series of seminars have quickly become a favorite of mine, and I think this is also the case for many people in the community. So it's really an honor and a pleasure to be here, and I hope you enjoy and you find interesting what I have to say today. So please let me share my screen. Oh, where is it now?
We tested it.
Okay.
Before,
yeah, but now
like babies,
you know, this
sure.
this happens.
Never works when we need it to. It's fine.
Yeah. Okay. Just a second.
Sure. Take your time. It's fine.
It went away somehow. Okay, it should be cool now. Okay, here it is.
Excellent. Yeah, I can see.
Okay, sorry for the delay. Okay, so today I'm going to talk about some applications of quantum computing that we have been exploring at CERN. But before I start, I want to give some context. I want to give a warning or a disclaimer about what kind of project I'm going to be talking about. Of course, I'm not going to be exhaustive by any means. There are many things going on at CERN related to quantum technologies, and in particular also to quantum computing. So I'm not by any means going to mention each and every project that is going on or has been going on in the last few years. I'm going to, of course, focus on those projects in which I have been involved directly as part of a collaboration of my group here at the University of Oviedo, which is called the Quantum and High Performance Computing Group, which is a quite small group by the usual standards. We are, I guess, like 4 or 5 senior researchers plus 3 or 4 PhD and master students, which is not much, but we are very passionate. And last year, around March, I think, we started this collaboration with researchers from CERN openlab to explore together the possibilities of applying quantum computing to different tasks in high energy physics and also beyond high energy physics. I will be also talking about this. And I think this collaboration has been very fruitful for both CERN and for us, for sure. And we have developed several different projects, and we are working in different projects with many different institutions that I have tried to list here. Maybe I missed someone, sorry about that, but we are working with, for instance, Cambridge Quantum Computing, with several universities, including ETH Zürich and the École Polytechnique at Lausanne, the University of Cambridge, also people here at Spain, at the University of the Basque Country, well, and other departments at CERN, like, for instance, the BIMS department. And I think this has been, of course, very interesting and very fruitful. We have communicated our results in several different international conferences. We have published some results in international journals, and some of them are also available at the archive. And I have tried here to select some of the ones that I think will be more interesting for the people following these seminars, because they are more related to high energy physics. Although at the end, I will also showcase a little bit of other projects that we have been working. So this is kind of the context of this collaboration and who we are here at the University of Oviedo. But one question that I think should also be addressed is why quantum computing in collaboration with CERN, okay? I'm not going to go into much detail about this because earlier this year, Alberto Di Meglio, who is the head of CERN Open Lab and the director of CERN's Quantum Technology Initiative, also gave a very interesting seminar here and explained the motivation for all this. CERN data processing needs are huge. It is estimated that when the particle collisions are going on, more than 1 petabyte per second of data is produced. And of course, it is a challenge to store, to analyze, and to process all this data. Okay, so CERN has been always looking for new solutions in computing in order to deal with all this data and to extract as much information from this data. And several years ago, particularly at CERN Open Lab, several different projects related to quantum computing were started in order to assess the possibility of using quantum computing for different high energy physics tasks. And this crystallized last year in the creation of what is called the Quantum Technology Initiative, which is now something going on, very formal, which has this goal for the next few years of, among other things, exploring the potential of quantum computing in high energy physics. I'm not going to explain all these objectives. Alberto Di Meglio gave a very interesting talk, as I mentioned, and you can if you did not attend that seminar, you can watch the recording. But I want to mention that there are several different parts in this quantum technology initiative related to quantum computing, to quantum sensing, to quantum communications, to quantum theory. I'm only going to focus on the part of quantum computing. That's why I mentioned at the beginning that by no means I try to be exhaustive and to list each and every project that is going on related to quantum technologies at CERN, okay? And in particular, I want to focus on the kind of project that we are developing in collaboration, my group in collaboration with CERN Open Lab and all these other institutions, which tends to be a kind of project in which the practical results are paramount. So we know that nowadays we don't have fault-tolerant quantum computing or scalable quantum computers. We have these small, noisy, intermediate scale devices, but we also want to try what is possible to do with this kind of hardware that we have today. So this is not only something that we do with pen and paper and calculations, but that we want to try. And I will try to address how each of these projects is being brought to quantum hardware and what are the results that we expect to obtain in that regard. And with this context, I think I can now start focusing on several different projects. I have selected a few, and I will focus on 3 of them. I will mention some others at the end, but I have selected 3 that I think will be especially interesting to the people who usually attend these seminars, because they are strongly related to different high energy physics problems, okay? And there is also a common factor to all of them, which is the use of quantum machine learning, okay? And well, it was nice while compiling all these results and trying to select what to talk about today. It was nice to realize that we've been working in this application of quantum machine learning to high energy physics, and we have been kind of working on every different branch of machine learning or quantum machine learning in a way, okay? Because you know that machine learning can roughly be divided into 3 main parts: unsupervised learning, supervised learning, and reinforcement learning. And I will be showcasing a project of quantum machine learning, which we are doing together with CERN and these other institutions in each of these branches of machine learning. Okay, so to start with, I want to focus on a supervised machine learning problem, which is a classification problem. I won't go into much detail here because this is quite related to something that was also covered in one of the first seminars in the series by Professor Xiaolan Wu, because this is a problem of classification of events in collisions of particles in which we want to detect whether a Higgs boson was created through this channel or not. Okay, so you can see here the Feynman diagram that we are interested in. And in the positive cases, in the signal cases, a Higgs boson is created, while in the other cases, a gluon is created. And this is quite a challenging problem because, as you can see, the final state is exactly the same in both cases. So we need to take into account several different physical variables, in this case, 67 physical variables. And we want to explore the possibility of using quantum machine learning classifiers in order to distinguish when we have a signal event and when we have a background event. Okay, of course, this is something that we can do directly with classical machine learning, and this is something that, of course, has been done. And for instance, deep neural networks and boosted decision trees offer quite good performance here. I'm showing some cases in prior to this project in which these kind of techniques were applied, and I'm showing here as a summary of the results the ROC curve that were obtained with these methods. Okay, just in case you don't work with this kind of diagram, let me remind you that this ROC curve somehow evaluates the trade-off between false positives and true positives when we move an acceptance threshold in the classifier. Okay, so if we tend to accept many different events as positive events, then of course we will have a lot of true positives, but we may also introduce a lot of false positives. Okay, so the ideal classifier should have low false positives and high true positives. So it should be something around here. If we are close to this corner of the diagram, then the classifier is the better. So a common way of measuring the quality of a classifier is to draw this curve with the different points, with the different rates of true positives and false positives, and then calculating the area under the curve, what is usually called the AUC, and the higher the better. Okay, so you can see here that we have different classifiers, different methods. The one that achieves the best results is this deep neural network. And here we can also see that these methods have been also tried with a previous reduction of the number of variables that are considered. Okay, so it's good to keep this in mind in order to compare these results, which are done with a lot of training examples, so almost 2 million examples in this case, to compare with what we have obtained with quantum machine learning with much less events, okay, training events. Okay, so the kind of techniques that we have been using are two of the most popular in the quantum machine learning community, which are the quantum version of support vector machines and the quantum version, so to say, of neural networks. Okay, so just as a quick reminder, a support vector machine is a classical method in supervised learning in which we try to separate events or examples from two different classes with a hyperplane, and we try to maximize the margin between the hyperplane and the closest examples from both classes. And this is something that, of course, we can only do when the data is linearly separable, okay? But we can expand somehow the power of these support vector machines by considering a future map that embeds our data in a higher dimensional space. So maybe in that higher dimensional space, we can find a linear separation between the data. Okay, and this gives rise to the possibility of also using quantum computing techniques to do this kind of classification, because what we can do is to somehow embed our classical data into a Hilbert space by means of using a parameterized circuit with some free parameters that we use to map our data into this Hilbert space, and then we can calculate easily this quantity, which is the absolute value squared of the dot product of the embeddings of this data. Okay, and this is what is usually called a kernel. And what is nice about support vector machines and their quantum version is that you only need to compute this quantity in order to train the model and do the classification. Okay, so that is what we do here. And the rationale for trying this idea is that maybe when you work in a Hilbert space, which is much higher dimensional than your classical data, you have access to highly entangled states that are not easy to simulate classically, and you can get better performance in your classification. So this is one of the models that we are using. And the other one is also based on the application of parameterized quantum circuits, but here we use these variational forms in two different ways. We have the feature map to embed our data again in this Hilbert space, and we also have a trainable part, which is called usually the variational form, that we try to optimize in order to get a classification, a result when we measure some observable of these states that we prepare, that somehow separates the signal from the background. Okay, so we do a training that is similar to the one that is performed with classical neural networks by computing gradients and backpropagating and all that. And then we obtain the best parameters for this variational form. And when we have new data, we can just embed the data using the feature map and then classify by measuring this observed. Okay, so this is more or less what is being tried also in other different fields with the help of these quantum machine learning techniques. And in our case, we have also added a new so to say, way of dealing with the data. Okay, because as I mentioned previously, we are much focused on trying our models and our projects with real quantum hardware. And the limitation of the number of qubits, the limitation in the depth of the circuit with this kind of models leads us to do some dimensionality reduction in order to have the possibility of dealing with the data with these reduced models. Okay, so we have tried different ways of reducing the data. For instance, autoencoders. We have also selected the most informative variables and keep only those. For instance, computing the AUC that we get when we use just one variable. We have also used this technique, which is called data re-uploading, which uses the same variational form, the same feature map with different data somehow sandwiched with the variational form. So we have tried many different ideas, many different ways of reducing the data, many different variational forms in order to test whether we can, with a reduced model and with less training data, somehow achieve the same results that we know that we can obtain with classical models. Okay, so just let me quickly summarize our best results so far. So we have here the results with quantum support vector machines. In this case, well, after trying many different architectures and many different models, the best one was obtained with amplitude encoding as the feature map. So with just 6 qubits, we can encode 64 different variables. Remember that we had 67, so we had to drop the 3 less informative variables. And we have always compared these models with classical models with the same number of training examples. Notice here that we are only using 576, which is much less than the 2 million, almost 2 million that I showed at the beginning. So we tried also different classical models with the same number of events. And the reason for using only these events is that the training of these models with quantum simulators takes a lot of time. It's not feasible to go up to this huge number of training events. We have also tried these variational quantum classifiers, or these quantum neural networks, with different variational forms, different ways of encoding the initial information. The best results that we have got are the ones in which we have used a set feature map, a 2 local variational form, 4 qubits, and 8 variables. The 8 variables were selected, previously selected by their AUC. And since we have 8 variables and we have 4 qubits in this case, and we are using a set feature map, we need to use data reuploading. Okay, so we have 2 different variational forms and 2 different feature maps with different parameters. Okay, so these results are kind of satisfactory in the sense that, well, they are close to what we can get with classical models with the same number of training events, but they are not so close to what we know we can get with the full training set. Okay, so we also try different ways of trying to achieve the same results or close to the results that we obtained with the full training data set. And for this, we tried a hybrid architecture in which, instead of first selecting the variables or reducing somehow the dimensionality of the data with autoencoders or whatever, we trained together the reduction with the quantum classifier. So here we have a hybrid model in which we have a classical dense neural network, which goes from the 67 variables down to 8. And then together with this, so this feeds the results directly into the quantum part, we train this classifier, which is similar to, well, I think it's exactly the same architecture that we got here, okay? And this got us the best results so far. We are still investigating different ways of doing this classification, but you can notice here that we now go almost up to the point which we were able to reach with classical models with just 2000 events, okay? Well, it also must be noted that with these 2000 events, with classical methods, we can get something similar, okay? But well, at least we know that we can do this, or we can reach results that are similar to the ones obtainable with classical methods. Okay, so this is one of the projects. If you want to know more details about this, there is this paper available in the archive. And of course, I will be happy to answer any question at the end of the seminar, or if you want to reach me by email. I want to now move into another different project, which is also related to quantum machine learning, but in this case to an application of unsupervised learning. In unsupervised learning, we do not have labeled data, like in the case of the classification. In the classification, we have the 67 variables for an event, and then an additional label that tells us whether this is a signal or a background event. In the case of unsupervised learning, we don't have this feedback. We don't have this label. We just have a collection of data that comes from some underlying distribution. And our goal is to somehow learn something about this distribution. Maybe we want to estimate parameters of the distribution, or like in this case, we want to be able to sample, easily sample or efficiently sample new data that comes from an approximation of this probability distribution. This is something that has been done in different ways, but probably the most popular one is what is called generative adversarial networks. I'm sure you have heard about this because they have become very popular, especially to produce images that are indistinguishable from real images. This has been applied, for instance, by companies like NVIDIA to produce these images here of people that do not exist. So these are all completely generated by these neural networks, okay? So this is something that is done with this architecture that I'm showing in the slide, with this structure of the generative adversarial network, in which we have a discriminator and a generator, okay? And these are, in the classical case, these are neural networks that are trained alternatively with competing goals. So the discriminator has the goal of distinguishing real images from the images that are generated by this generator, while the generator tries to fool the discriminator into believing that the images that it produces are real ones. Okay, so this is sometimes tricky to train, but if you do it correctly, you can get impressive results like the ones I was showing in the previous slide. And this is something that had already been tried in a high energy physics settings in order to produce images of the calorimeter output when you have collisions between particles, the energy deposit along the trajectory of the collision as detected by this calorimeter output. This is an image from a project that was developed at CERN openlab, classical generative adversarial network that is called the 3D GAN. And as you can see, the images that are generated with this model are almost indistinguishable from the real images. Okay, so this is something that has been quite successful in this application developed at CERN openlab. And the idea was to try to do this with a quantum version. So you can do a quantum version of the generative adversarial network by replacing one or two of these neural networks with a quantum neural network with one of these variational forms. Okay, so that is the idea. There were several different proposals of how to do this that came almost at the same time. And before I joined, or before we started the collaboration with CERN openlab, they were already developing this idea of using a quantum generative adversarial network to generate these kind of images. And in this work, mainly developed by Sujong Chang from the École Polytechnique at Lausanne and by Sofia Vallecorsa at CERN openlab, they managed to generate images which are similar to the ones obtained in real collisions, but with a simplification of the setting. You see here that the resolution is much lower, and also with a kind of a limitation. In this case, what was generated was the mean image. Okay, so it was a generative adversarial network, a quantum GAN was used to generate these images, but since they were using just one variational form, they were producing just the mean image of all the training data that they had. So the idea here was, in collaboration with Cambridge Quantum Computing, to develop a new model in which we can overcome this limitation of just generating a mean image. So we want to generate different images that can be cannot be distinguished from the ones obtained in real collisions. And well, the model that we came with replaces the generator with two different quantum circuits, parameterized quantum circuits, and keeps the discriminator as a classical neural network. Each of the quantum circuits uses this kind of variational form, repeated with different layers, and each of them has a different role. So what we call PQC1, the parameterized quantum circuit 1, has the goal of generating a basis vector that somehow selects the image that is going to be generated by PQC2. Okay, and then PQC2 generates, it's similar to the former circuit that was used in this previous project, generates an image. Okay, here we need some technical details. We need to extend the number of qubits with some ancillas in order to have enough degrees of freedom to generate images that are not orthogonal to each other. I will point you later to our paper in which we explain all the details. And after some hyperparameter scanning, and after some problems with the training, because this is a little bit tricky to get right, we came with a situation, or with an example of one of these quantum GANs, in which we can successfully generate images, but in a simplified setting. Okay, so we had to simplify the problem to just one dimension with 4 pixels, which is, well, kind of a toy problem, but it's what we need to do in order to be able to train this correctly and for it to be feasible with the simulators that we have now. We trained it with 20,000 images, which were clustered. Here you can see the different clusters, not for the training, but just to compare the representatives or the mean images in each cluster to the images that we get later, because we selected here the number of qubits for the image to be 2, so we have 4 pixels. Here the number of qubits that we feed into this circuit to be 2, so we have 4 different images that we can produce. So our goal is to see if we can produce images that are close to these ones here. And in this case, after some hard work, we were able to obtain something that converges and produces images that are, well, quite close to these ones here. So we are quite proud of this model because it was a bit tricky to train. And now we are in the process of moving into proofs or experiments with real quantum hardware. We have tried different models of noise with our simulators in order to check whether the hyperparameters need to be changed. So we are expecting to produce new results soon. Also, in the previous project that I mentioned, the one in which we classify different events, we are also in the process of trying noise models in order to move into real quantum hardware experiments. Okay, so, well, you can see here the different collaborators that we had in this project. And again, this is something that you can check in more detail in our paper that is available in the archive. Okay. And
so, Elias, I take this moment that you're transitioning to give you the 10-minute warning that you asked.
Okay, so I will try to go faster. Thank you. Okay, so that the last project that I want to showcase in more detail is a quantum reinforcement learning project that we have been developing together with, well, of course, CERN openlab, my group at the University of Oviedo, and together also with the beams department at CERN and with the Polytechnic University of Bucharest. And as I mentioned, this is a project that uses quantum reinforcement learning. And if you don't have not worked with reinforcement learning, let me quickly mention that this is a way of doing machine learning in which you don't have data at the beginning. In supervised learning, you have labeled data. In unsupervised learning, you don't have labels, but you have a lot of data. In reinforcement learning, what you have is an agent that interacts with an environment and gets performs some actions and gets some rewards, okay, in response to these actions. So the idea here is to try to maximize this reward in order to solve some task. The task can be navigating a maze, can be playing a board game like chess or Go or something like this. Or in our case, this can be just a problem in a toy problem in particle accelerator control and in beam steering in one of these hadron colliders. Okay, so the idea here, this is a very simplified model. We are now working with more complex ones, is that we have a beam of particles that we want to steer on target. So we have the state of the beam, which is measured by this position here. We have a dipole magnet that allows us to steer up or down the beam, and then the target, the reward, is how close we are to the target of this beam. Okay, so we integrate how much there is an overlap of the beam with the expected target. Okay, and we have implemented this as a OpenAI gym template, which is like the standard in reinforcement learning. And we have framed this as an episodic task in which we want to, starting from a random position, steer the beam in target by moving it up or down and under. Okay, and we have done this. Well, I think I will skip these details. We have done this by comparing what we can achieve by using a neural network and what we can achieve by using a quantum Boltzmann machine, okay, which is an analogous of a classical Boltzmann machine, whose free energy can be used to approximate the maximum reward that we can obtain when we are in a given state and we perform a certain action. Okay, so this is what in reinforcement learning is usually called Q learning. We have this approximation of this Q function. And when we know this Q function, or we have an approximation of this Q function for a given state, we can try the different actions, in this case, moving the beam up or down, and see which is the one that gives us the highest reward. Okay, so we have tried this, and we have implemented this with a classical neural network. And I guess the main point here is that, well, we are able to solve this problem. It's an easy problem, very easy problem, but it requires on the order of 300 or plus interactions with the environment. Okay, so situations in which we need to move, see what is the new reward, and use this to train the model. While when we use the quantum Boltzmann machine that we train with several different options, we train this with either simulated quantum annealing or with real quantum annealing on a D-Wave computer, but this is quite expensive in cost, in money. So we alternate both things. We sometimes train the model with the real quantum annealer, and then we evaluate the performance with simulated quantum annealing. These are the results that I'm showing here. And we are able to solve the task with much less interactions with the environment. So on the order of 120 or something like this. Okay, so this is something that is quite successful or quite satisfactory, and it's promising. We are now trying different versions of this model with a continuous action, also with a continuous state. The one that I'm showing here is with a discretized states and action, which is only going up or going down. And we are also trying a much more complicated situation in which we have 10 dipole magnets and a more complex problem. Okay, but well, I think this is something that is quite interesting and quite promising. And we presented these results at the Bristol Quantum Information Technologies Workshop early this year, but we will probably be submitting a paper or maybe uploading it to the archive later this year with the new developments. Okay, so this was all that I wanted to mention regarding projects related to quantum machine learning and more focus on high energy physics applications. But we have also, in this collaboration between the quantum and high performance group here at the University of Oviedo and CERN openlab, we have been working in other projects which are not so closely related to high energy physics, but have the common factor of being quantum computing oriented. Okay, so well, I will just mention briefly that we have been working in quantum random number generation. This was part of a project that we also started together with Cambridge Quantum Computing to assess the possibility of using quantum random number generators in Monte Carlo methods. But as a preliminary study, we wanted to see how good are the random numbers or the random bits that you can obtain with a simple approach, which is just using a Hadamard gate and then measure. Okay, and we realized that with actual quantum hardware, well, not even 40% of the sets of bits that you can get pass a simple test of uniformity. And we developed some methods that, well, are not perfect, but can increase the possibility of passing or the probability of passing this test to more than 80%. So you can check more details in this paper, which is already available at the Journal of Supercomputing. We have also studied the influence of the choice of classical minimizer in the quantum approximate optimization algorithm, together with a former student of mine, Mario Fernandez Pendas, which is currently at the University of Basque Country. And we realized, we noticed, we discovered that the choice of the classical minimizer has a lot of influence, especially not so much in the quality of the solution that you get, but the time that you need in order to obtain those solutions is can be really very different. So maybe you want to select a gradient-free minimizer in which you don't obtain the best performance in terms of the final result, but you can run this setting a lot more times and try to get a better solution. Okay, so well, this was kind of the conclusion of this study. We have also studied a generalization of the famous Deutsch-Jozsa and Bernstein-Basirani problems. So this is a purely theoretical paper in which we generalize these promise problems, and we showed that they form kind of a natural partially ordered set in which the Deutsch-Jozsa problem is maximal and the Bernstein-Basirani problems are kind of minimal. Okay, and what I like the most about this paper is that we were able to show that although these problems are always solvable with just one query in a quantum computer, with a classical algorithm, a deterministic classical algorithm, the range of complexities that you may find are all the way distributed all the way from 1 to 2 to the n minus 1 plus 1. Okay, so I think this is kind of nice. Also, I want to point you to this paper that we published with a report on a series of online lectures that I had the pleasure of designing together with the CERN Quantum Technology Initiative and developing and giving online last year. The reception was truly exceptional. We had, for instance, in the first lecture, more than or almost 1,500 people attending live. And the feedback that we obtained was really very positive. And we summarized the methodology and the results of this experience in this paper that is already available at the Journal of Supercomputing. And to finish, I don't know if I'm on time. Well, I think a minute above time, but I hope it's not much to ask to introduce this last project, which is I think the most recent one that we have started, that we call Project ABAQUS. And I think this is the first time this is mentioned outside CERN. So this kind of exclusive presentation for you. And this is a project in which we are developing a benchmarking framework for software quantum computing tools and also for hardware devices, either quantum simulators or classical simulators or quantum real hardware. And the idea here is that we have an easy to extend foundation in which we can, with which we can define benchmarks both for different frameworks. Now we are contemplating Qiskit, Penny Lane's CERC, but we want to extend it to any other interesting quantum computing framework, and also hardware benchmarks for different devices, from laptops to supercomputers to hardware, real quantum hardware. And to collect all these tests that can be easily run by anyone that is interested in benchmarking their system, to collect these results and to make informative reports. Okay, so this is a sneak peek of what the web app in which we will show these results will look like. You can see that we can select different tests. So far, we have only implemented these simple ones, but this is easy to extend. The number of qubits, the different frameworks, the versions, and all that, and then you can get a score of the results in that particular setting. Okay, so this is, I think, nice and useful if you want to select the best framework or the best device to run your experiments. And this has been mainly being developed by my student Samuel González Castillo, which I think is here attending the Zoom meeting also, supervised by Alberto Di Meglio, Sofia Valecorsa, and myself. And I guess that, well, our goal is to release this to the public in November, and we will also release this white paper or report on the structure and architecture of the ABAQUS framework soon. So, well, that was all I wanted to talk about today. Thank you so much for your attention, and I'll be happy to answer any question that you may have.
Thank you very much, Elias, for this very nice talk and sharing all this impressive work. So indeed, we have time for questions. I think, Rafaela, people can now unmute themselves if they want and can raise their hand. For those in the YouTube live broadcast, you can type a question in the chat if you want. but here in the Zoom, just please raise your hand. Let me see if I see someone. So Elias, actually, I wanted to ask you, you've done this comprehensive work exploring the potential of quantum computation for all these different problems in high energy physics with different approaches. After this 1 year or more or I think more actually, on all these fronts, how do you see this field and its future and its potential?
Well, I mean, it's difficult to know what is going to happen, but I'm quite optimistic about the future. I think that we now have not only some evidence in form of these results with toy problems, but we are starting to see theoretical results that have been published recently that support the idea that, for instance, quantum machine learning can outperform its classical counterpart in several different problems. So I think that, well, now we are limited, of course, by the noise and the size of the quantum hardware that we have available, but I'm quite confident that we will find real applications in which we can outperform classical computing, maybe not in the in 1 or 2 years, but maybe in 5 or something like that. So, well, after all this exploration, I'm even more optimistic at the beginning. Thank you very much. So I would invite people also, if they want to comment. That's the advantage now with the Zoom platform, is it's two-way communication. So feel free.
Maybe I have a quick follow-up question. To which theoretical results were you referring at right now, saying that we start to have theoretical results that quantum machine learning outperforms classical ones? Can you elaborate on that? Oh, yes. For instance, there's been this work by people at ETH Zürich, in which they show that deep quantum neural networks can somehow or have a higher feature information than classical neural networks. Okay, I don't know if you are aware of this result. Also, I have not been able to read in detail a new paper that came out maybe 2 or 3 weeks ago by researchers at IBM, in which they show that for another case I think it's also in classification, some quantum machine learning methods can theoretically outperform the classical ones. So I think we are starting to see this kind of result, which is, for me, amazing. I mean, it's very encouraging to keep on working like this. I can send you the references. But no, that's fine.
Okay.
I just wanted to know if there were others.
No. As far as I know,
but I didn't know.
Well, as far as I know, those are the main ones. Okay, but yes. I'm sure more will follow.
Indeed.
Any other questions or comments? So as I was saying, the advantage now of the Zoom platform is that we can have a more interactive discussion. So we want this seminar also to be a forum for discussion. So anyone is welcome to intervene either with a question or a comment or answer. So if not, we are actually approaching the end of the seminar. So then I would thank Elias again. Thank you very much for your very nice talk. And I would ask Rafaela if she could share the slide with the announcement for the next speaker. So we're resuming our monthly seminars. And so on the 6th of October, we'll have Carl Jensen from DESY. We'll be talking about the title is From Tensor Networks to Quantum Computation of Lattice Field Theory. So quantum computation and quantum simulation of such theories. And finally, I would like to thank you all for participating. I think this went very smoothly. Thanks a lot in particular to Rafaela and Sagar, who organized the Zoom and YouTube logistics, and of course also to the co-organizers of the seminar, Andres, João, and Simone. So thank you very much, everybody, and see you on the 6th of October for the next talk. Have a good day. Bye-bye.
Bye, thanks.
Bye-bye.